let's look at the Pandas data structures now. Now, series is the first data types that we want to look at. A Pandas series is a one-dimensional array with labels that can contain any data type. We primarily use them for handling time series data. Creating a series is really very simple, just calling pandas.series on a Python list or NumPy array. So S is the variable that we want to store this series, 1, 2, not a number, 4, 5. If you print it out, notice that it's automatically indexed, and these are the number, and the data type is the float 64. Every series has a name. We can give the series a name as a parameter, or we can define it afterwards by directly accessing the name attribute. In this case, we have given our time series no name, so the attribute should be empty. So if we print s.name, you get none. Now this name can be directly modified with no repercussions. S.name is equal to toy series, and once you print it, this is the name that you get in return. Now we call the collected axis labels of a series its index. And index can either pass to a series as a parameter or added later. Similarly to its name, in the absence of an index, a series will simply contain an index composed of integers, starting at 0, as in the case of our toy series. So when we print s.index, it will get a range index starting from 0 to 5 as a step of 1. Now Pandas has a built-in function specifically for creating date indices, date_range is called. We use the function here to create a new index for s. So the new index is this. So Pandas data range or date range from 2016 January 1st, and the period is equal to the length of s, however long s is, and the frequency is daily. So when you print the index, you notice that it's generated for you, and it's actually a date time, data type 2016 January 1st, 2nd, 3rd, on it goes, and the frequency is daily. An index must exactly be the same length as the series itself. Each index must match 1-to-1 with each element of the series. Once this is satisfied, we can directly modify the series index as with the name to use our new and more informative index, well, relatively speaking. So basically, we take the new index, which we generated here or created here, and we basically store it into s.index or replace the s.index with the new index and print it out, and you get exactly the same as the new index. The index of the series is crucial for handling time series, which we will get into a little later. Now let's look at how do we access the series elements. Now series are typically accessed using ilock or lock. We use ilock to access elements by integer index, or we use lock to access the index of the series itself. So let's print the first element of the series, which is 0, and let's print last element. Again, is the length of it minus 1. We've done this before in the previous NumPy lecture. Is exactly the same. So that print out the first and the last. We can slice a series similarly to our favorite collections, Python list and NumPy arrays. We can use the colon operators to indicate the slice. This basically says from all the way to the beginning, all the way to 2, except for 2. So basically, we get the first 2 here. When creating an index, we have the option of specifying a beginning, an end, and a step. The slice will begin at the start index and take steps of size step until it passes the end index, not including the end. So we start at 0, and the end is the length of it minus 1, and the step is 1. So start, end, and step, and you get everything with the exception of the last one. 5 is not included here, as you can see. Right. We can even reverse a series by specifying a negative step size. And similarly, we can index the start and end with a negative integer value, much like this, and basically reverse the whole series itself. This returns a slice of the series that starts from the second to last element and ends at the third to last element, because the fourth to last is not included, taking steps of size 1. So here we're looking at -2, starting from -2 to -4, but this is in reverse. Okay, so because it's in reverse, Remember, we'll just take this as the example. We'll start from -2, okay, which is this one here. -4 is this one, but because it doesn't include that, so we ended up with 4 and not a number. We can also access a series by using the values of its index. Since we index as with the collections of dates, we can look at the value contained in as for a particular date. So basically you .log instead of ilog, and this is basically pointing it to the numbers itself, which row it is, whereby log itself is accessing the contents of the index itself. So we're using the date, which gives you 1. So we can also, even for range of dates as well, we can access the range of dates by specifying the beginning and the end. Don't do that. And you get the January 2nd all the way to January 4th data being returned to you. With series, we can just use the bracket to access elements, but this is not the best practice. The brackets are ambiguous because they can be used to access series and data frames using both index and integer values, and the result will change based on the context, especially with data frames. Let's look at Boolean Index. In addition to the above mentioned access methods, you can filter series using Boolean arrays. Series are compatible with your standard comparators. Once compared with whatever condition you like, you get back yet another series, this time filled with Boolean values. So we want to print all the elements we want to compare all the elements, whether it is actually less than 3 or not. And what you get is true, true, the rest are false. We can pass this series back to the original series to filter out only the elements for which our condition is true. So if we put s.log with the Boolean condition or comparators, what you get in return is actually those two that are less than 3. So if we so desire, we can group multiple conditions together using the logical operators and, or, and as well as this, and, or, and not respectively. This is called not, and what you get is this. So here you have less than 3, and also it's bigger than or greater than 1, so you ended up with this value here. It is exceedingly convenient for getting only elements of a series that fulfill specific criteria that we need. It gets even more convenient when we are handling data frames. Indexing and time series. Since we use series for handling time series, it's worth covering a little bit now how we handle the time component. For our purpose, we use Pandas timestamp objects. Let's pull a full time series, complete with the appropriate labels by using our getPrice method. This is only built in into the Quantopian research platform. All data pulled with getPricing or using our pipeline API will be in either series or data frame format. We can modify this index however we like. So we're looking at CMG is the symbol. We're providing the start date, the end date, and the prices is getPricing, providing the symbol CMG, start being the start, end date being the end, and the price that we're looking for is price only. We can display the first few elements of our series by using the head method and specifying the number of elements that we want. The analogous method for the last few elements is tail. Right, we print the type first. That tells us it's actually series, Pandas series, and we print the prices for the so-called prices, the first 5 elements, and this is what you actually get here. As with our toy example, we can specify a name for our time series, if only to clarify the name the getPricing provides us. Now, if you type prices.name, you get this interesting equity with the bracket 28016. This is the sit. This is actually the symbol. So if we just want to access the symbol, because this whole thing doesn't make any sense or hard to read, you just prices.name, it equals to symbol, and what you get is actually just CMG only. Right, let's take a look at the so-called data time index of our prices time series. Now remember, we extracted, I think, 3 years of data, 2012 all the way to 2016, 12, 13, 14, 15, so 4 years of data. And when you print it out, you notice that it's 2012 January all the way to 2015 December 31st. Note that this datetime index has a collection of associated information. In particular, it has an associated frequency, FREQ, and an associated time zone, which is UTC. The frequency indicated whether the data is daily versus monthly versus some other period, while the time zone indicates that locale this index is relative to. We can modify all of these extra information. If we resample our series, we can adjust the frequency of our data. We currently have daily data, excluding weekends, because get pricing pulls only data from market days. Let's upsample this daily data to monthly data using the resample method. So if we resample prices with the notation of M, what you get is that this whole thing becomes monthly data. Notice that it's January, February, March. These are monthly data. The resample method defaults to using the mean of the lower level data to create the higher level data. We can specify how else we might want the upsampling to be calculated by specifying the how parameter. We can specify median, which gives us a different value from this. We can even specify how we want the calculation of the new period to be done. Here we calculate a custom resampler function. This is our customized function that will return the first value of the period. In our specific case, this will return a series where the monthly value is the first value of that month. So here we have array underscore like with bracket 0. So the how is your own function, okay, and basically just return the so-called value of the first month. We can also adjust the time zone of a series to adapt the time of the real-world data. In our case, our time series is already localized to UTC, but let's say we want to adjust the time to be US Eastern. In this case, we use the TZ convert method. Since the time is already localized, we just take prices dot TZ convert to US Eastern, and basically what you get now is the US Eastern timestamp. In addition to the capacity for time zone and frequency management, each time series has a built-in reindex method that we can use to realign the existing data according to a new set of index labels. If data does not exist for a particular label, then data will be filled with a placeholder value. This is typically numpy, not a number, though we can provide a fill method. The data that we get pricing only includes market days, but what if we want prices for every single calendar day? This will include holidays and weekends, times when you normally cannot trade equities. Let's try this. We create a new datetime index that contains all that we want. So basically this is how we create it, start to end and daily. Okay, so this will include every day. Now let's use this new sets of dates to reindex our data time series. We tell the function that the fill method that we want is forward filling. That's what ffill is. This denotes forward fill. Any not a number values will be filled by the last value listed. So the price on the weekend or on the holiday will be listed as the price on the last market day that we know about. So prices reindexed to calendar dates, which is this calendar dates. So we're reindexing to this and forward fill any dates that we don't have a number. Now when we print the actual head, the first 15 values, notice that all of the data has been filled. Now we take 15 because obviously some of these are weekend. Okay, weekends only, working weeks usually is only 5 working days, and Saturday and Sunday usually don't have data. So one of these must be data. So here, January 1st is obviously holiday, Feb 2nd is also a holiday, so hence it doesn't have any number. Because we're forward filling, we don't have any historical previous market data to actually extract from, hence it becomes not a number. You notice that we still have a couple of not a number values right at the beginning of our time series. This is because the 1st of January in 2012 was a Sunday and the second was a market holiday. Because there are earliest data points that we don't have any information from before them, they cannot be forward filled. We will take care of these not a number values in the next section when we deal with missing data, which is right here. Missing data. Whenever we deal with real data, there's very real possibility of encountering missing values. Real data is riddled with holes and Pandas provides us with ways to handle them. Sometimes resampling or reindexing can create not a number values. Fortunately, Pandas provides us with ways to handle them. We can have, or rather we have two primary means of coping with missing data. The first of these is filling in the missing data with fill not NA. For example, say that we want to fill in the missing days with the mean price of all days. So fill not a number with calendar prices mean. Okay, we just take the mean and fill in the numbers. So now you have these two numbers, which is the mean of the whole time series. Fill NA is fairly easy. It's just a matter of indicating the value that you want to fill the spaces with. Unfortunately, this particular case doesn't make a whole lot of sense for reasons discussed in the lecture on stationarity in the lecture series. We could fill them with 0 simply, but that's similarly uninformative. Rather than filling in specific values, we can use method parameters similar to how reindexing method works. We could use backward fill, where not the numbers are filled with the next filled value instead of forward fill, last filled value like so. So we use backfill, so basically we take the next time that there is a value and fill it backwards. And hence these two values, the first 2 days, is the same as the third day's price. But again, this is a bad idea for the same reasons as the previous option. Both of these so-called solutions take into account future data that was not available at the time of the data points that we are trying to fill. In the case of using the mean or median, these summary stats are calculated by taking into account the entire time series. Backward fill is equivalent to saying that the price of a particular security today, right now, tomorrow's price. This also makes no sense. These two options are both example look-ahead bias using data that will be unknown or unavailable at the desired time and should be avoided. Our next option then is significantly more appealing. We could simply just drop them. By using the drop not a number method, this is much better alternative than filling not a number values with an arbitrary numbers. So just use drop NA and that first 2 days disappeared. Now our time series is clean for the calendar year with all of our NaN values properly handled. And it's time to talk about how to actually do time series analysis with Pandas data frame. Now time series analysis with data frame, we can plot it out and just have a look at what it looks like. The title is the name of the company plus prices, and as you can see, it's very easy to plot the charts using Pandas. Just add the dot plot after the data frame or the Pandas variable itself. As well as some built-in descriptive statistics, we can either calculate these individually or using a describe method. So we can calculate the mean or standard deviation by print them out, and or we can just dot describe, and gives you the number of so-called count or the number of so-called data points that you have, the mean, the standard deviation minimum, 25th percentile, 50th percentile, 75, and also the maximum. Now we can easily modify a series with scalar using our basic mathematical operators. Take the price, multiply by 2, minus 10, and that's what you get. Or we can recreate linear combinations of series themselves using basic mathematical operators. Pandas will group them up, matching index, and perform the calculations element-wise to produce a new series. If you take a moment to think about this, this is really quite amazing. It just matches the index yourself without you having to do it. Imagine doing this using Excel. You have to first match the series or the index itself before you perform the calculations. And here, you just need one line. Take the price plus 5 times the randomly generated number. Make sure the index matches plus 20, and you get the actual price itself. If there are no matching index, however, we may get an empty series in return like so, okay, which is not a number. Okay, rather than looking at time series itself, we may want to look at its first order difference or percentage change in order to get additive or multiplicative returns in our particular case. Both of these are built-in methods. We can either calculate difference, okay, or we can calculate percentage change. Now, why from 1 onwards and not from 0 onwards? Because once you actually calculate difference, the first one will always be not a number. We'll plot that, and you will notice that this is actually the so-called, what are we looking at? The mult returns, which is the percentage change, multiplicative return, and this is what it looks like. Pandas has convenient functions for calculating rolling means and standard deviations as well. If you are a trader, you will probably think of simple moving average. This is really the way to do it. This is a 30-day rolling average using Pandas. Rolling mean, this is the so-called variable name, and how wide is your window. You specify 30 here and store it into this variable and plot the rolling mean. And this is what you get. You plot the price first, and then you plot the rolling mean on top of it. You can also plot the standard deviation. Calculation of rolling standard deviation is done exactly the same way. And once you plot it out, this is what the standard deviation looks like. This is a 30-day rolling standard deviation. Now, many NumPy functions will work on series the same way that they work on one-dimensional NumPy arrays. So this is mult returns. Remember, this is the percentage change. The median of it is this number. The majority of these functions, however, are already implemented directly into series and data frame itself. So you just take mult returns, dot method, median, and you get the number right away. In every case, using the built-in Pandas method will be better than using the NumPy functions on a Pandas data structure due to an improvement in performance. Make sure to check out the series documentation.